And clearly, there are a group of people, very smart people, they are not happy with the situation, right? Because they consider this is unfair, and the Wall Street they get an unfair advantage versus normal people, right? So they don't want they want to develop a system that the normal people can basically won't be ripped by the system. So that is they try to remove those central intermediaries, right? Because as long as you have central intermediaries, then you have no control over them. But if you don't need a central intermediary, then you need a distributed ledger. Ledger you can consider is a bookkeeping, right? Because you need to actually have a record, right? Like a database, who owns what, right? So that is a ledger, right? But here they use a ledger as a term here. Right? And also, because it's distributed, you need to make it public, right? So that we can prove, right, whether this record is correct, right? Because also you need it to be public so that we can reach a consensus, right? Because if you only have a single centralized ledger, then everyone can refer to that one, right? But if you have a distributed one, they may have different record, right? Which one should you use? Right? Also, there is a privacy issues from here. Okay, so the very high level idea is that so they will record all the transactions in blocks and then chain them together so that it is called blockchain. Right? In the Bitcoin design, so every 10 minutes, they will create a new block. And the new block size is 1 megabyte, I believe, right? So it can contain 4,000 transactions. And on average 10 minutes per block. So basically you can do the math, right? So roughly 7 transactions per second. So the system is very slow. This is very different from like Ethereum or other blockchains. So that's also partially the result, the reason. Now Bitcoin is more like a reserved asset versus something that you can use for the real a lot of transactions. That's something we can talk later. So basically here you can say the transaction can be like A send 1 Bitcoin to B send 0.5 to C, and C send 2 Bitcoin to D, something like this. Right? So within each block, you will see tons of transactions. Right? Okay, so the challenges here are 4 of them. Right? The first one is verification. Right? To make sure the transactions is valid. Right? If A want to send 1 Bitcoin to B, then we need to know that A actually holds at least 1 Bitcoin, right? So that he can send it to B. The second one is to avoid double spending. Right? So even though A have 1 Bitcoin, we should avoid that A send it to B at the same time send it to C or send to D. Right? In a centralized database or ledger, this is easy to avoid. But in a distributed one, that is not so straightforward, right? Because the different ledgers, they may have a different view of the system state. So this gives it seems that there will be some opportunity, right? In some of the ledger, you can spend the Bitcoin, send it from A to B, while in some others, you can do that from send from A to C. And you hope that if they don't find out the problem or too late for them to find out the problem, then you can basically double spend your money. But if someone can double spend the money, then the system will collapse, right? So it is very important to avoid double spending. So as long as you see some news saying that one blockchain has a double spending problem, if that's true, then it's a disaster for that blockchain. Actually, last year, there's some news about on Ethereum, they have double spending, right? But actually, after some investigation, people find that it's not true, right? So that's why the system is still working normally. The third one is incentives. Why we need incentives, right? So if you have a central entity like the bank also have incentive to do all the transactions, to do all the bookkeeping. Why? Because you need to pay them some fees in order to do that. Here, if you need distributed ledgers, then you need to find some way to incentivize those distributed ledgers, right, to provide the service. And the last one is that because you provide incentive, and the incentive is non-trivial, then you need to decide who you should give the incentive to for each block, right? So basically, whoever create each block will get the reward. So you need to, so more than one will want to get the reward, right? So you need to decide who should create each block and then to get the reward. Okay, so far any questions? Okay, if no, let's continue. The first one is for the incentives. Right? This is a reward for creating a new block. So at the beginning, so it get 50 Bitcoin per 10 seconds. Right? For each block, the reward is 50 Bitcoin. Right? So this halves every 4 years. Right? So you can do the calculation. 50 times 6 that is for each hour, times 24 times 365, and then that's for 1 year and times 4, right? Then the first 4 year, this is amount, and the second 4 year, only half, the third 4 year, only fourth, right? So you add them together, you see this is actually, it's converged, right? So it's a bounded, upper bounded by roughly 21 minutes, right? Which means for Bitcoin system, so the total supply is 21 minutes. So this is very different from the traditional bank system. For example, no one can restrict how many US dollars the Federal Reserve can print. Actually, nowadays they even not printing, right? You know that when they do QE, what they do, right? They just add some number to their database. And so nowadays creating new money, you even don't need to pay the cost to print the physical money, right? So that's really easy to, you can go anywhere, right? But here in blockchain system, so normally the total supply is fixed, so no one can change it. So now if you count, right? So from beginning 2008 is 50 Bitcoin per 10 minutes per block. Nowadays, it's 0.6.25, right? So last year when I gave the lecture, it's a 40K per each Bitcoin. Now it's 20K roughly, right? So even at 20K per Bitcoin, so the reward to create each block is still more than 100K, right? So it's significant. Therefore, we will have the next question, right? So which miner, right, should we give it to? So in order to decide which miner, because there are a lot of miners, so they use something called proof of work or POW. So the mining details. So the hash function is widely used here, right? Basically means the hash function is to convert a string of any length into a fixed length string of bits. For example, one function can convert Bitcoin into a sequence of bits. Right? So there is a particular hash function they use that's called SHA 256. Right? So the number basically means the sequence of bits has a fixed length of 256. So the hash function need to satisfy the following property. So do the forward calculation is easy, right? So give me the Bitcoin, the string, to calculate the bits, it's very easy. But the backward calculation, you give me the sequence of bits, ask me what is the original string, that is extremely hard, right? Let me give you an example. This is the equation, right? So a lot of mathematical calculation of x, you get y, right? Going from x to y is easy, right? But going from y, given your y, to solve x is extremely hard. Right? For example, try if y equal to 10, try to solve for x. Right? So that's the basic idea of the hash function. So in a block, right? So the header has a the header is a string, right? So it contains the header of the previous block and timestamp, a random number. Of course, this is a hash, right? So hash of this, and we actually do twice of the hash to make it even safer, right? So you get the hash for the header. And in order to create a block, you need to find a random number, right? So that the requirement is this hash of the first n digit should be all zero. For example, n can be 66. Right? Depending on how many miners they have. So basically, the larger n you have, the higher requirement you get. Right? So the more miners you have, you should increase n so that on average, after 10 minutes, one miner can get the number. Right? On the other hand, right, if someone say, I get the random number, right, so that I can get the hash value with the first n digit to be all zero, it's very easy to verify, right? Because the header string, except the random number, is public, right? Then you can plug in the random number and do twice of the shard to 256. Then you get a hash value. You can just check whether the first n digit are all zero, right? So verification is easy, but finding that random number is hard. Any questions? Okay. So far there is no easy way, efficient way to do that. So the basic way is just to random try, right? You find get one random number, try it, right? So on average, right, you say for each digit, the first digit to be to have zero, because there are two possibilities, either 0 or 1. In order to get one digit to be 0, you get a probability of 1/2. Right? So if you need the first 66 to be 0, the probability you get is 1/2 to the power of 66. Right? So on average, you know that you need to try 2 to the power of 66, this number of trials, in order to get one. Right? So that the more you can try, the more likely you can get this the right random number. Right? So that your winning chance will be proportional to your computing power. Right? That's why people are building those very powerful mining farms. Nowadays, a lot of them, for example, in Texas, even in New York, right? So they are not doing any fancy work, right? So they basically just try random try. Right? So this is actually a very embarrassing parallel algorithm, right? So basically, if you have one machine, right, you can just try those numbers. If you get two machines, you can just ask them to each try different set of random numbers, right? So it's perfectly proportional to the computing power you get. Right? So this is an extreme case of parallel computing. Right? So your